Okay, welcome everyone. Today, the IQuest summer seminar, the speaker is Eric Chitambar. He's a professor from Department of Electrical and Computer Engineering of UIUC. Today, his talk is about quantum resource theories. And just a kind of reminder, please turn off your microphone and video during the talk. And feel free to type in the questions in the chat, or maybe just free to ask Eric. Eric, is that fine during the talk?
Yeah, that's fine.
Okay. All right.
So if I don't see the chat, KG, just stop me at any point.
Okay. Okay. You didn't see the chat. Okay. Fine. I can do that. All right. So okay, it's all yours, Eric.
Okay. Great. Okay, thank you. So I'm very excited to give the seminar today. And as I was putting together my slides, I thought it would be good to maybe have a more introductory level discussion here on quantum resource theories. And because I know we have a wide audience of people tuning in here. So consider this to be your introduction to quantum resource theories, rather than a list of technical results. Hopefully this you'll at least, if you have no experience working in this area, you'll at least walk away with a sense of what a quantum resource theory is, why it's interesting, and why it may be important to the work that you do. Okay, so this is introduction, so I'm going to cover like the broad landscape, but I also want to highlight some results. And in particular, I have two of my collaborators on the front page here. Part of the reason I put this picture on, because I thought it was cool that we had a picture with all of us together. But I am going to cite some work that I've done with Francesco and Gilad. Okay, so let's jump into it. Basically, there's 5 areas of this talk. First, I'm going to motivate the resource theory philosophy. I call it a philosophy because it's kind of like a framework or an approach to analyzing problems. And I want to motivate this from a thermodynamics and also a statistical decision problem perspective. Then I'll define what a quantum resource theory is, introduce some of its features, have a brief discussion on the difference between a static and dynamic resource theory. Then I will look specifically into a quantum resource theory of measurement compatibility or measurement incompatibility. So that'll be a bit more detailed. And then finally, I'll have a few things to say about current work going on in my group and future directions. All right, so let's begin with some thermodynamics here. I'll consider a very simple thermodynamic system, which is just a cylinder, and there's a piston attached to it. There's a fixed number of particles in the cylinder. For simplicity, assume they're all the same species. And this system now is just characterized by 2 parameters. U would be its energy and V its volume. And we can talk about a state transformation of our system. And because there's only 2 parameters characterizing the state, it's just a transition from one set of coordinates, VU, to another set. All right? So this is referring to as a state transformation. And in principle, we can realize any state transformation. So if we plot UV here, we can go from any V1, U1 to any V2, U2, provided that we can put in an arbitrary amount of work or extract an arbitrary amount of heat. We can realize any state transformation. But usually what we're interested in are the state transformations that are achievable if there are certain restrictions on what we can do. Okay, so if there are physical restrictions on our processes, then that will impose limitations on the state transformations we can achieve. And specifically what I want to consider here is adiabatic processes. Okay, so what sort of processes are this? Somewhat, you have to be careful the way you define what an adiabatic process is. So I'm going to use the description as follows. So what are we allowed to do? And I'll put in quotation mark 3 operations here because we're going to see this theme again and again. What are they allowed, the 3 objects we can do? So we can introduce any device that's in some initial state. All right, this device could be a motor, a heating plate, anything that's going to interact with our system. And then we will interact the device with the cylinder. But what we'll do is we'll attach a weight to the device. So this weight here can go up or down, and there's some gravitational field here. And what that will do is that's this motion of the weight then is going to power the device, which then will interact with our cylinder, and that'll cause our state transformation. What we require though is at the end of our process, the device returns to its original state. Okay, however, the weight may have moved up or down. And the whole idea here is that we're trying to capture the state transformation that it can be entirely accounted for by the mechanical energy of the weight rising or falling. Right? So you can think of just this device as what it's doing is it's capturing the change in energy of the weight and it's converting it into a state transformation of our system. Okay, so that's what we're allowed to do. And then we can ask the question, what state transformations are possible by such a process? We'll use some notation here. Let's say that we can go from x, if we can transform x to y by an adiabatic process, then we'll have this ordering. And what you probably know from basic thermodynamics is something known as the entropy principle, where you can transform x to y if and only if the entropy of y is not less than the entropy of x. Okay, this is the second law of thermodynamics. All right, now note here, one comment is that this relationship between x and y, this is what's known as a total ordering. And the reason it's a total ordering is because I just have to compare two states, x and y, look at their entropies. And they're either going to be the same or one is going to be larger than the other. Right, so this provides a total ordering on the states that we can achieve. All right, so that's an adiabatic process. So keep sort of this principle, this idea of transforming under restrictions in your head. I want to turn to another problem, which on the surface looks entirely different. New symbol. What symbol? This here? Jim?
Yeah, I'm unmuting myself. Yeah, what does that symbol mean?
So it means this. Take this as your definition. So when you see this symbol, it means you can transform x to y by some adiabatic process.
Okay, so it's like
just take that as a definition.
Yeah, all right.
Okay, so now I want to switch domains. Consider something that looks different on the surface, but I will argue that it looks similar, or that in fact it has a similar structure. And this is a statistical decision problem. All right, and now here, the problem is as follows. So you have some source, and it's a stochastic source. So I put a categories dice here, but it could be anything, any random process. And the outcome will be x here. So this is what the dice lands on, or the outcome of your event. And then what happens is your outcome is subject to a noisy channel. So all this means is this n here is just describing a transition from x to y. So if it were noiseless, then you would have y equals x, but in principle there could be a bit flip or some noise that it's introduced, and then you have a transformation. And then the experimenter here observes y and makes a decision, which is going to be z. So applies some function onto y, and then reports this z to some referee where a payoff function is awarded. And this payoff function is a function of the decision made by the experimenter and the original output of the experiment. Okay. And so if our source is uniform, then the average payoff, and suppose there's a finite number of outcomes, the average payoff is just this. Right? So what we do is we just randomly choose one value of x, we apply the channel, we apply the decision function, and we get this average payoff. All right, now it's a payoff, and so the experimenter here is wanting to make as much money as possible. So the freedom that the experimenter has is to choose a decision function. And he or she will choose a function that maximizes the average payoff. So we can write this as for some fixed channel n and a payoff function. Sorry, that should say payoff, not loss. The maximum average payoff is given by this quantity here. So we're maximizing over all decision functions. All right, this is sort of the most amount of money that the experimenter can make on average, given one particular payoff function and one channel. Okay. All right. So this quantity, this dollar max is useful for us because it provides a figure of merit for the channel. For every payoff function, we get some figure of merit, and it's essentially how much the maximum amount of money that a player can make for that particular payoff function. Okay, so given that this is a figure of merit for a channel, we can ask how this quantity changes as we transform our noisy channel n from one channel to another. We go from n to n. And I want you to think of this as being analogous to a thermodynamic state transformation. Okay, so in thermodynamics, we went from one state of the cylinder to another. Here we have a noisy channel n, and we're transforming it to another one m. And we're going to ask, how does this quantity, this dollar max, behave under such a transformation? All right. And just like in the thermodynamics situation, it's going to depend on the type of channel transformations that we allow, right? We had to look at the adiabatic transformations to get the entropy function. Here we need to look at a specific type of channel transformation to get a useful function for us. So what are we allowed to do? What are our restrictions? Here the operation is very simple. We will allow additional post-processing of the channel. So what I mean by this is, here's our input-output channel, our original channel. And what we can do is we can connect a second channel, K. All right, and this is post-processing because we're taking our output data and we're going to scramble it to get a new value, Y prime. And if we combine these, then what we have is a full channel that's going from X to Y prime. So this is what we're allowed to do. We're allowed to realize channel transformations by this post-processing operation. All right, and intuitively, if we can go from n to m, we'd say that channel n is more informative than m because we're introducing this noise here that's scrambling the original information that came out of n. Okay, and so in terms of this game here, it's basically we've now plopped a post-processing function here. All right, so this problem has a long history in statistics, and a famous result known as the BSS theorem characterizes this transformability from one channel to the other. So the statement is that you can go from n to m if and only if you're able to, the maximum payoff for all payoff functions of n is no less than m. Okay, and note here that this forms a partial ordering compared to the entropy formula because here we have to check all payoff functions. And remember, these payoff functions, I'll go back to the picture, the payoff functions came right here, and in principle, we could choose any function here that's a function of x and z. And the theorem says that only if n is larger than m for all payoff functions can we construct a post-processing channel that takes us from n to m. Okay. All right, good. So that's statistical decision problems. Now, this is a quantum seminar, so now I want to move us into quantum mechanics. And so the problem I want to consider here is a quantum entanglement transformation. So here we have two quantum systems controlled by Alice and Bob, and choose your favorite pair of quantum systems, like two photons. And their initial joint state is some vector psi AB, which could be any realizable states. In general, it won't be entangled. So what I mean by that is you can't write it as a product state. And suppose they want to convert their system into some other state. So they want to go from psi to phi. All right, now, if we allow any sort of interaction between the systems, then in principle, we can always realize this state transformation. But we're not interested in the full totality of operations. We want to focus on a limited subset of operations. So what are we allowed to do? What are these limitations? And so this is the operational paradigm that we consider, where Alice and Bob are spatially separated, so they're in different laboratories. And what we allow them to do is sequentially perform local measurements or local operations on their subsystems, and then communicate classically between one another. So you get something that looks like this, where Alice makes some measurements on her subsystem, communicates it to Bob. So M1 is the outcome of her measurement. And then given that information, Bob does something on his system, and it kind of goes back and forth, like a ping pong, bouncing back. But the point is that each of these boxes here, these are only acting on locally on their respective subsystem. Whereas the communication between them is classical, and this is what's correlating their operations. Okay, so these type of processes are known as local quantum operations in classical communication, or LOCC. So now let's go back to our question. And we wanted to go from psi to phi, and let's use this notation again. We'll say that psi is related to phi if psi can be converted to phi by LOCC. And so a theorem which is due to Michael Nielsen provides the conditions for when this transformation is possible. So there's a set of functions, and these functions don't need to worry about the details, but they're here if you want this to see it. There's a set of finite number of functions you need to check, and if your functions are non-increasing under this transformation, then in fact you can construct an LOCC measurement that does the trick, that makes the transformation. Okay, and again, now this is a partial ordering on entangled states because there are more than one function you need to check, whether the order is, whether one is greater than the other. Okay, so this is kind of the summary of part one here. So we've looked at, does LOCC allow post-selection? Yes, it does. Yeah, but what I would say, Paul, is that in this situation where we're specifically looking at a pure state to pure state transformation, and so if you're doing some sort of post-selection, then you're in the mixed state regime because you need to average over the thrown away outcomes. Okay, so to review, summarize what we have here is there are three different problems here, and the structures are similar. We're talking about converting one object to another, and we've characterized the convertibility in terms of these functions. In the thermodynamics case, it's entropy. In the channel post-processing, it was these payoff functions, and in LOCC convertibility, it was these entanglement functions here, these EKs. All right, so two lessons, take-home lessons. First lesson is placing constraints on physical processes leads to a partial or even a total, perhaps a total ordering of objects. Okay, so physical constraints lead to introduces some sort of ordering. And the second lesson is that when you place these constraints on processes, it leads to certain quantities that cannot be increased. And importantly, these quantities you can interpret as being quantifying some sort of resource. Great. Okay, two questions coming in, but let me just hammer home these lessons. Okay, so restrictions on your physical processes leads to partial ordering, and then you get these quantities which we can interpret as somehow identifying resource in our states. Okay, Marius, what happens if you place LOCC with very small entanglement? Yes, you can do that. Then you would get another class of operations. You would be restricted with epsilon entanglements, and Nielsen's criterion, that theorem would no longer hold. So there'd be some other condition. Okay, and going back to the definition on the Chi-Fan norms here. So essentially, I'll just give 20 seconds of detail on this. So you have a bipartite state psi, and what you do is you trace out one of the systems. So you look at the reduced density matrix, and then you consider the eigenvalues of that. And this down arrow means that you order them in non-increasing order. And so for each k, you take like the k smallest guys, because you're summing from j equals k to the dimension. We can chat a bit more about that. It's after the talk. Okay. Good. So hopefully now your curiosity is piqued a bit on these similar structures that we've seen, and in fact now we will generalize to the idea of a quantum resource theory. And before I do this, I'm going to go kind of quick here, just because I don't want to dwell too much on this, but I've been using this language, quantum operations, and I just want to make sure so that we're all on the same page, like what is a quantum operation, and I apologize for those who can just tune this out for 30 seconds or 2 minutes. And so in general, a quantum operation describes the most general evolution of a quantum system. And the way to think about this pictorially is that you have some quantum system S, and you can ask, all right, what can we do with S? Well, the answer is we can do everything quantum mechanics allows. And so what is that? Well, you can axiomatically write down what quantum mechanics allows, but the idea is that we can do the following. You can always model every process as this, in this form, where you introduce some ancilla system R. Right, so you start out with S, you have some extra system R, then you turn on some interaction Hamiltonian for some given amount of time, and that causes a joint evolution. And then once that's done, then you measure a subsystem. Okay, and when you make this measurement, you extract some classical data from your system, but you might have some post-measurement quantum data left. And so what you get is a hybrid classical and quantum system. And so this is really what a quantum operation is. And mathematically, we describe these things by completely positive trace preserving maps. So, but you can think of this just as like a black box here, where you have a quantum system input, and then it has an output. Sometimes it's convenient to break the output into a classical system and quantum system. Other times it's not, and we can just group them together and just say we have this input-output relationship, which is described by a completely positive trace preserving map. Okay, so that's what I mean by quantum operations. That's what we mean in the literature when that terminology is used. Okay, so and it's important to understand this for the definition of a quantum resource theory, because a quantum resource theory consists of two components. So the first component is a set of density operators, which you can say denote by F, and S is just the system that we're looking at. And a collection of quantum operations. So these are these completely positive trace preserving maps that are going from one subsystem to another. And the key restriction here is that for all of our maps that are in this set O, it must act invariantly on these sets F. So for any density matrix that starts out in F, when I act on it by E, I'm going to end up in F as well. Maybe the system may change. I may go from S to S bar, but I've identified a set of free states or a set of density matrices in S bar. So I'm just going from F to F. And so I use the word free states. In fact, this is what we identify these states as. The elements of F are free, and the elements of O, these maps are free operations. Any state that's not in our set F are called resource states. So here's the picture. You can kind of, if you don't want to keep your mind wrapped around all the symbols, this is the picture to keep in mind. So you take your set of states here and you chop it up into resource states and free states. And here's your S bar, here's another system. And you have a map, and what the requirement on the map is that whenever you start off in a free state, you have to end in a free state. Right? You can start off in a resource state and go to a resource state, or you can start off in a resource state and go to a free state, but you must map free state to free state. And that's the minimal structure of a quantum resource theory. So once you have these ingredients in place, then you have a well-defined resource theory. Okay. So let's look at this in action a little bit. One of the nicest examples of a quantum resource theory is entanglement. And so here, the free operations are LOCC, which we described earlier. And the free states are those that can be generated by LOCC. So what I mean by generated is you have Alice and Bob in their separate labs. They do some state preparation. So Alice prepares her system in row A, Bob in row B. And then they do one of these ping pong protocols where they make local measurements and exchange our information classically. This goes back and forth. And at the end of their protocol, they get something that looks like this. It's some mixed state. And we can define the whole set of states that can be prepared in this way. And these are what's known as separable states. Okay, and so this then defines for us what entanglement is. And I want to emphasize the point here is that this is an operational definition. And we say a quantum state is entangled if and only if it cannot be generated using LOCC. So I guess like this, the perspective or the philosophy here is that we've defined some resource entanglement with respect to the operations, LOCC. So it puts the physical operations on somewhat more of a more fundamental level. And from these operations, this resource entanglement has emerged. Okay, so this is the example of a resource theory. Maybe kind of, let me take a step at a higher level and ask the question, why bother with resource theories? What's interesting here? So I'll give you a few reasons. First are some practical reasons. So this selection of free operations. Now when we defined it, in principle, it could be any class of CBTP maps, any subset of them, but typically for this to be of any practical value, you choose them to reflect some realistic experimental conditions. So in LOCC, this is a reasonable class of operations to consider because you're not forcing your Alice and Bob to exchange quantum communication between their systems, right? In classical communication is easier for us to perform than quantum communication. I mean, we're engaged in a classical communication right now over Zoom, and that's relatively cheap for us. So LOCC is a natural class of operations to consider from a pragmatic perspective. And so then the question is, what can we do under our limited operations? And well, this is what a resource theory studies is. You've restricted your operations, what can you do? What sort of quantum information processing? It also allows us to quantify the resourcefulness of the different quantum states. And we'll talk a bit more about this quantification in a few slides. And it allows us to identify methods for transforming one to the other. So we looked at that in terms of these state transformations. And those all came out using tools of resource theories. So those are some practical reasons. It's fundamental. Well, as we saw on the previous slide, it actually allows us to define some primitive features of quantum mechanics like entanglement and nonlocality in terms of this operational context. And it also allows for a unification of different aspects. So we've seen similar structures that have emerged in thermodynamics and entanglement, but this is characteristic of resource theories in general, of finding these common features and being able to borrow techniques that were used in the study of one resource and apply them in the study of another resource. There's a question. Is there a resource theory for states which are easy produced using certain devices? I would say yes, there is. I guess it would depend on your device. So if you're looking at an ion trap or photon source, yeah, you could do it. But if you're asking, has it been done? I don't know. I don't think so. I haven't seen it, but that would be, sure, you could do that. I guess your operations there would have to be chosen appropriately.
Yeah, but that might make it interesting for connection with experiments, right? If you can do
absolutely right.
Certain things are possible at the moment, you could develop a resource theory which reflects that. Of course, this will not be forever, but it gives an umbrella to do this.
Yeah, yes. Good. Marius, I realized that maybe that was just the private chat question, but Marius' question was whether there's a resource theory for states which are easy to produce. And so if you have some experimental device that's a source that produces states, does that lend itself to a resource theory? And yes, it would. Okay, so here's a non-exhaustive list of resource theories that have been studied in the literature. So we looked a bit at entanglement and asymmetry, athermality has been studied. This magic states, this is studied within the context of quantum computation. So here your free states are which are known as stabilizer states, and your free operations are stabilizer operations. And a way to think about this is that these stabilizer operations, these are operations that you can simulate efficiently using a classical computer. So your resource in this framework here are states whose simulation we don't believe can be done easily on classical computers. So this is a nice resource theory because it studies the resource of quantum mechanics for quantum computation. There's been a lot of work done on quantum coherence, for instance. I've worked quite a bit on this resource theory. And there have been a number of resource theories that are more intimately linked to study quantum foundations. I just throw this list up here just to indicate to you guys that it's been a very active area of work for the last 5 to 10 years. Okay, let me highlight some advantages or some common structures of looking at a resource theory. So first is in terms of quantification. So how do you quantify the amount of resource contained in a given state? Someone prepares for you a state and asks how much resource is in it. You want to be able to provide a well-meaning number in response. Yes, it is. Yeah, okay, maybe I'll come back to that question at the end of the talk, but the short answer is yes. Okay, so in general, there will not be just one single way to measure resource. And think of this like when you're trying to define distance in a metric space, there's not one unique distance. It's just some function that satisfies a set of properties. Likewise for measures of resource. But one property that all resource measures must satisfy is what we can call the golden rule of resource. And what this says is that the function cannot increase under your free operations. So if we apply, here's our free channel here, we're guaranteed that phi is monotonically decreasing under that operation. So examples of this were the entropy, or rather minus the entropy in adiabatic, the max payoff in channel post-processing, and these entanglement quantities and LOCC convertibility. A general recipe for building resource measures, well, one approach is distance-based. So here, I like this because it's very easy to conceptualize. You have your set of states, and you have your free states here, you have your resource states here, and then you define any distance measure on your set of density matrices. And what you do is you say, okay, with respect to this measure, I want to find the closest free state. So I minimize this distance here. And that provides for us a resource measure. So some examples of this was if you let your distance be the trace norm or the one norm, so basically you're looking at this rho minus omega and you're minimizing over all free states. This gives us one quantifier. A more commonly studied measure, for good reason, it has a nice operational interpretation, is this relative entropy of resource. Now here, D itself is not a true measure, a distance measure, but it is good at quantifying how close two density matrices are. So this D is relative entropy. And I won't get into that now, but it's a very important resource measure for operational reasons. Okay, and so another nice advantage that we have in this picture is that we can use techniques from convex analysis to identify witnesses for detecting resource states. So essentially, if you have a convex set of free states, and when you have any state that's outside that set, you can find what's known as a separating hyperplane. which in this case is W is just some Hermitian operator. And it has these nice properties that if we take the trace, the inner product of W and any free state omega, we always get something that's non-negative. But with rho, we get something that's negative. Okay, so why is this useful? Well, what we can do is, if W is a Hermitian operator, so it's an observable for us, so we can just interpret this as just an expectation value. And if we have a given state and we compute its expectation over, we do many measurements of this observable, if its average is less than 0, then we in fact know that we have some object that is resourceful. So this provides a way for detecting the resource state. Okay, good. So I want to switch just a little bit here and talk about this distinction between static versus dynamic resources. So most of the previous discussion has been in terms of static objects. And a static object is just a state. You think about, you have a quantum system and you take a snapshot in time and you describe what that is. The description would be a density matrix. A dynamic object is a channel. So this is something that has an input and an output, and it's defining the relationship between the input and output. And first point is that the resource theory formalism can be extended to the study of channels as well. And this is important because actually, like all of information theory can be seen as a dynamic resource theory of communication, where the noiseless channels have maximal resource, right? Because your goal here is to communicate from one party to another noiselessly, and so the objects that have the most resource are the noiseless channels. And so now to extend our resource theory formalism, now what we do is we go up to a higher level. So we think of states as being channels, and our free operations are devices that will transform one channel to another. All right? And in the literature, these are sometimes known as supermaps or quantum cones. And so let me just kind of give a picture of what this is. So again, now change your perspective a little bit and think about, we have a channel and we want to convert it into another channel. So what can you do? Well, it's a nice result which says anything you can do can be described as follows. So you start off with your S to S bar channel. You introduce some pre-processing channel here. Then you have a post-processing. And then you connect it with some side memory. Right? And if you look at what happens, so now you have a T to T bar relationship, and this defines for you a new channel. So this is how you convert one channel to another using pre-processing, post-processing, and then you connect it with some side memory. A specific example of this are measurement devices. Okay, so what is a measurement device? Think about it as you're in the laboratory, you have some device that takes a quantum input and it gives you a classical output, which is your measurement outcome. But you also have some instructions that you can feed into your measurement device. So if you want an example here, this could be like Stern-Gerlach experiments, where rho is your atom spin going in, and your measurement instructions are the angle of a direction of spin you're measuring. So you're taking your magnet, you're rotating it. And then your outcome is then whether it's deflected upward or downward on your screen. But the claim here is that abstractly, any quantum measurement process can be modeled in this way. Quantum input, classical instructions, and then classical output. So this would be a QC to C channel. All right, this is a dynamic object. And so the question I'm interested in is what resources could be present in such a device? Well, one of them I'll identify as quantum memory. And where is quantum memory in here? Well, you could think about the device may need to store the quantum state until the measurement instructions arrive. So there's no guarantee that in fact the choice of spin will be arriving at the same time that your quantum state arrives. So if for this to work, you would want to have some sort of quantum memory here that can store rho until the instructions come in. And what I want to show you is that operationally, this is equivalent to the resource of measurement incompatibility. Okay, so what I want to do in the next few slides is make this link between quantum memory and incompatibility. So you've probably heard of incompatibility in the context of joint measurability. This is kind of standard quantum mechanics textbook stuff here. So as we know, observables have this feature that the order in which you measure them affects the statistics. So if I first measure A and then B, I get some probability distribution on the outcomes P1, whereas if I measure B and then A, I get P2. And in general, these will not be the same. And we say that they're incompatible if P1 is not equal to P2 for some input state. And what this means from an information theory perspective is that you cannot define a joint probability distribution. So again, going back to Stern-Gerlach experiments, you can imagine first you measure your spin in the Z direction and then X, and you get some probability of outcomes for the Z and X spin, or you can measure X and then Z and you get something different. Okay. And the theorem is that these are incompatible if and only if they don't commute. And so for observables, incompatibility is equivalent to non-commuting observables. And you can see this if you look at the converse, so that if they do commute, what does that mean? Well, that means that they're simultaneously diagonalizable, right? We can find a common eigenbasis. So let the PAs and PBs be the common eigenprojectors. And then we define a third observable, C, which is just projecting into the common eigenbasis. And so what you can do is you can take rho and you first measure C, and then you get some outcome K, and you can send it then to one of two channels. If it's the A channel, it performs one particular type of processing. And if it's the B channel, it provides another form of processing. And really all this processing here, these channels, this is just coarse graining, right? Because the PAs, these are built up from the rank 1 eigenprojectors here. So the takeaway message here is that it's once I have K, then I can get my outcome A, or it would be equivalent as if I had measured A by doing some sort of post-processing here. Likewise with B, I do another set of post-processing. All right. Another way of putting this into a form that resembles our original problem is that you can think about this as this process is not needing quantum memory. So I have my state rho, I measure C, I get outcome K, and then I store that in classical memory until I make the choice of which observable I want to perform, whether A or B, right? And then I feed this into this classical post-processing channel, and then I get out C, right? So K is stored in classical memory, and this allows the instructions to be, classical instructions X to be delivered asynchronously with respect to the quantum system. All right, so this definition, so that was for observables, but we can generalize it to POVMs as well, which are just like generalized measurements, and you get the same structure. But in contrast, if you have incompatible measurements, then you can't model your measurement device in this way. And the reason is because the choice of measurement depends on your measurement instructions X. So you have to line these things up so that both your instructions and your quantum state arrive to your POVM or your measurement within the same time frame. Okay, so here's the summary here. These are the two pictures that kind of gets to the point here. Compatible measurements, they don't need quantum memory for asynchronous control. So when I say control, I'm referring here to the choice of measurement. So this is like your classical instructions X. Whereas for incompatible measurements, in fact, you do need that because you can't measure rho until you get the instructions X. So this is the link between quantum memory and incompatibility. All right. Okay, so suppose now you build in the laboratory some classically controlled measurement device. So I put kind of a gray box here. I don't really care what's going on underneath the hood. All I care is that you have some channel that has quantum classical input and outputs a classical data. And what we're interested in is to fully characterize the operational power of this object without having to introduce any additional quantum memory. So we've built this thing and we want to know, great, what can we do with it? I don't want to have to go and buy more quantum memory. I just want to use what I've constructed. I have some very fancy experimental technique going on underneath the hood. What can I do with this? And this is, in fact, a resource theory question, because here the resource is the quantum memory. We don't have this freely available to us. We just want to use the device that we built. Okay, so now let's kind of put these various ideas together. And so what we have, this is what we built here. And we want to convert it into something else. And we want to use our the free supermaps that are compatible with this resource. So we ask the question, what are we allowed to do? So we start off with our measurement device. We introduce some classical preprocessing. We can do some quantum preprocessing. We can take our classical and have a side channel. So we have classical memory that connects it to a post-processing operation. And in total, then we get some new channel M, some new measurement device. And crucially, the point I want to emphasize here is that for this to fit within the resource theory framework, we're not introducing any quantum memory here. We're just, the only memory involved is the classical memory. So here's our proposal for a resource theory of incompatibility. The free objects are compatible families of measurements. And then here's our free operations, which we can collectively describe as compatibility preserving. And now we can ask the question that we asked at the beginning of the talk, except now in this particular context, if we can convert one measurement device N to another by M, let's use this relationship, say this ordering here, and we'll say N could be converted to M. And we want to answer this question, when is it possible to go from one measurement device to another? Okay, so let's recall now. This is the second example we looked at in this talk for the statistical decision problem. Basically, we framed it as some payoff function, which is a function of both the output of the channel and of the original source. So we want to generalize this now. We want to take the BSS idea and go now one level higher. And so this is what we think. We have some CQ source here. So the source now has a classical variable X, and then it also has a density matrix, rho and XY. All right, and this is what gets fed into our measurement device here. So X is the instructions. This could be spin direction or something. And then rho is prepared. It's a function of X and Y. We apply our measurement device. We get outcome A. Then the experimenter makes some decision function. Sorry, this should be a function of A here. And then there's a payoff function. And so a result that we were able to show, which generalizes the original BSS theorem in terms of convertibility using the free operations that we define, these compatible preserving supermaps, is that N can be converted into M if its payoff function is always as large as the payoff function for M. Sorry, the max payout is always as large for N as it is for M for all payoff functions omega. So this then, as I pointed out, it generalizes the BSS theorem by essentially adding now a quantum element to our source. Okay. So good. All right. In the last 10 minutes, I just want to highlight 3 current projects that I'm working on, and 2 are in-house here. So I want to give them some special attention. So this is a resource theory project, well, related to resource theories. It's done with Yuji and Shinan, who are graduate students here. And Yuji is in Gina Lorenz's group, and Shinan will be joining the PhD program in ECE departments this fall. So here's the problem that we have been considering. So it's a communication problem where you have N senders and you have 1 receiver. And the whole point here is we want to ask the question, how well can a single particle be used for this communication task? So in the spirit of a resource theory, what's allowed here? There's a particle source, and the particle can be sent down a definite path, or it can be sent down a superposition coherence. And these encoders, so A1, A2, they're all n parties, they have access to one and only one path. And they can perform some encoding operation with the restriction that it does not introduce new particles. So we call these number preserving operations. So these are like the free operations. And so then we analyze this divides a communication channel. And so we analyze the properties of this channel. And it turns out you can do quite a bit more if you allow for a quantum particle versus a classical particle. And the details are in this paper here. So I encourage you to read it. A related problem, which I'm working on with Brian Doolittle, is understanding classical and quantum communication with dimensionality constraints. So here's a situation where, again, we're setting up a communication channel from Alice to Bob. And now red is going to be some system that Alice sends to Bob with encoded information, but the key restriction here is that the dimension of the system is bounded. So we put a hard constraint on the dimension. And so to kind of stretch it into this resource theory language, what we're allowed to do is you can distribute shared randomness between Alice and Bob, but that shared randomness must be independent of the measurement of the message data. And then you're allowed to exchange a bounded dimension system. And so our analysis is relating the quality of communication you can achieve as a function of your dimension of your system. All right. Another resource theory project that I'm involved in right now is with collaborator Gilad Gore and two of his students. And here we're identifying the Bell non-locality of quantum channels. So I'll give a brief description of the overall idea here. So if you think about what a Bell experiment is, to look for a Bell inequality violation, what you're doing is you have some joint state rho AB, which may be entangled, and you feed it to Alice and Bob, who choose some measurement directions or some measurements to perform, X and Y, and they get out outcomes A and B. And everything is described nicely by Born's rule here. So these are the transition probabilities for giving the income measurement choices X and Y, outcome A and B. And we define Bell non-locality as being some correlations that can't be simulated using a local hidden variable model. So these correlations do not have this form here. And if that holds, then we say that we have non-locality. Okay, so that's the definition. But like from a resource theory perspective, you can think of this as a conversion from static resource to dynamic resource. So your static resource is this state here, and then you're applying some free supermap, and it's converting it into a bipartite classical channel. And this bipartite classical channel is one that can't be simulated by a local hidden variable model. Okay, so now our philosophy is, okay, now that we have this conceptual idea of Bell non-locality for states, let's elevate it to the level of channels. And so it's kind of very simple. Now we have some bipartite channel, and we are studying conversions using some free operations into classical channels. So basically this is the process that we consider, and this allows us to identify a resource in the bipartite channel, which we identify as the Bell non-locality of this particular channel. Okay, so that's pretty much all I wanted to say today. So I thank you, thank everyone for listening. And this picture here, so every 2 years there's a workshop in Seefeld, Austria, a quantum information theory workshop. And of course, it happened to be this year, but well, it was canceled. So this is my picture longing the Austrian Alps.
Thank you, Eric. Very nice talk. So there is a leftover question in the chat. You want to?
Right. So the first question is it possible to apply similar reasoning when considering as free the operations that use a polynomial of operations instead of exponential? And I believe I think the reference here, if I remember, was when we were talking about stabilizer operations. And yes, that can be done. So basically what you would do is you would fix your model of computation. So whatever model you choose, then you would define the states that can be prepared easily or the gates that can be simulated efficiently. Those would be your free objects. And then you would just proceed studying the resource with respect to those free objects and free states. Okay. Marius, what about additional classical memory?
Yes, maybe I can specify what I mean by that. So you had a characterization of these in terms of the supermaps from N to M.
Yeah.
But I think this was not taking additional memory, classical memory account, right? So you had a characterization for on the super level. When N goes to M, if and only assert, right, this theorem here. If you go back,
the BSS theorem.
Yeah, but did you? Right, so this is transforming these channels, but does this allow additional classical memory to be used?
In the original theorem, no, it doesn't.
But in your version, in
our version, it does, yes.
Right, so this theorem, that's what I meant.
Yeah.
Here you did not draw an extra memory.
Yeah, you're right, but it does. I just didn't draw space, but it does allow for classical memory.
Okay. And the other question I have is if you go to your last page.
Yeah.
So you have this, you know, well, yeah, not the last, this one. No, I think go to the channel version of that page.
This one here.
Yes. So if you have this bipartite channel, is it more than just looking at the Choi map and the channel and see whether that has some kind of Bell inequalities? Or, I mean, that would be a canonical candidate. You take the Choi matrix of your bipartite channel and then look at whether that matrix can be, this density can be used to prove Bell inequality violations. Is it more than that or less in this case?
I mean, so that's one way. I mean, the real subtlety here is in defining these supermaps. So you could look at the Choi matrix, sure, but then you would have to say, well, what's going to be my protocol for converting it into a classical channel?
Right, but did you say that explicitly in your talk?
No, I didn't. I didn't say that.
Okay.
I didn't say that. I don't. It's kind of a
that depends a lot on your
thing. I didn't want to get into it.
Okay. Okay. Good. That depends a lot on your blue arrow here, right? So.
Yes.
Okay, that makes sense.
Exactly. Yeah. That's in fact, that of our work, this is maybe the main thing we're focusing on is this blue arrow.
Okay. Great. Thank you.
Hannes, are there ways to compare QRTs? Yeah, so there's been some work, especially in thermodynamics, of going from like one resource to another. So you can look at like the union of two sets of free objects, right? So if I have a resource theory of entanglements, and I'll just reference coherence because I worked on that quite a bit. So you have a resource theory of coherence and resource theory of entanglement, and then you can consider trade-offs from one to the other. So you say, how much entanglement do I need to introduce to my system to bolster my coherence under some restricted set of operations, and vice versa. So yeah, there is this idea of exchangeability between different resource theories. You can do it as well. Okay, cartoon showing a connection between two systems. Oh, I know. Yeah, I got you. This one, yeah?
Yeah, that's it.
Okay.
Can you give an example of that?
Of this one to here?
Well, I guess so, because that certainly is not reversible, I guess you'd say, right?
Right, yeah, correct. That would not be reversible. Sure, so, I mean, decoherence, for instance, would be a great example of this. So you have some state you prepared in the superposition of say spin up and spin down, and you have some decoherence effects where now all of a sudden it's gone from this pure state superposition into a mixture of probabilistic mixture of up and down.
Okay, and so I should think about these resource states as being the ones that are have entanglement in them, and the free states as states that don't have any entanglement.
Exactly. Yeah.
Okay. All right.
That's right.
Are there any further questions from the audience? All right, so, all right, thank you, Eric. Thanks for the nice talk. So next week we will have Marius to give the seminar talk. So yeah, same time, Tuesday, 11 a.m. All right, so thank you, everyone.
Thank you, KG.
Bye.
Yeah, thanks a lot, Eric. Thanks.
Thanks.
Thanks, Eric. See you in a little bit.
Yeah,
Yeah.
see ya.
Eric.
Thanks.
See you, Jim.